let's describe a subsequent motion first. Got 2 kilogram block dropping on a spring. It's going to hit the spring and it's going to push the spring down until the spring slows it to a stop. And the spring is going to spring it back up. And of course, what's interesting is it sticks to it. So after that, it's going to bounce up and down. So the subsequent motion is going to be, it's going to skish it all the way down to here. It's really skished. And then it's going to pop back up. Now, when it pops back up, it's going to stretch. I'm not willing to discuss where it stretches to there. And then it's going to come back down. We're going to ascribe the half this distance as the amplitude, right, from some neutral point. The point that it's going to oscillate around is the point of equilibrium. And again, that's the point at which the net force is 0, right? It's not pushing up or pushing down. So when it goes past the point all the way back up, it's going to get pulled down. When it's on the bottom part, it's going to get pulled up or pushed up. Okay? All right, so that's our basic situation. So then it's first thing it says is determine the speed of the block right before it hits a spring. And this is one of the reasons why I think these problems are likely to be on the AP test. Oh, before I go any further, if you haven't done this problem, do it and then see what the problems are, right? Because I'm going to show you how to do all the problems. If you're just going, oh, that makes sense, you're going to get choked on this test. Okay, if this is on your test, which it's not likely to be, but feels spookily, logically like it might be. Okay, so it's determine the speed of the block. The instant it hits the spring, okay, well, it's fallen 0.45, so I'm just going to energy before equals energy after. Energy before is equal to mgh is equal to 1/2 mv squared. That's 2, 9.8. Height was 0.45 equals 1/2 2 times the distance squared, which is 0.45. I'm sorry, the velocity squared, which is what I'm solving for, right? Sorry, that's all jammed in there, but I hope you, by now, this problem should be pretty easy for you once I explain what it is we're doing. 2 times 9.8 times 0.45 divided by 1, 0.5. I get my velocity would be equal to 2.97 meters per second. Okay. Determine the period of simple harmonic motion for the system. Well, okay. Period equals 2 pi square root of m over k. That does not change. 2 pi square root, what's the mass? Mass is 2. The spring constant's 200. So that gets me 100, which is 10. So this is going to be 0.628-ish. Let me double check that just to make sure. Somebody's going to tell me, why isn't it 0.627-ish? I will double check. Divided by 10, bam. 0.628-ish. Good, I've got it. And that would be seconds, right? That's the period. Okay. Does not change because I drop it from outer space. Doesn't matter. Spring is going to bring it back and forth, no matter how much you get compressed in that same amount of time, as long as it's working like a perfect spring. Okay, determine the distance the spring is compressed at the instant the speed of the block is maximum. So maximum is going to be when it's passing through this middle point, the equilibrium, right? Because it has no forces on it, and if let's say it's on its way up, after that it's going to get slowed down. If it's on its way down, after that it's going to get slowed down by the spring getting squished. So the equilibrium point, wherever that is the point at which it's going to have maximum speed. Now, how do I figure that out? Well, I'm going to do energy before equals energy after. Now, I'm going to be incredibly lazy because the energy, I got to be careful. Let's not do that. I was about to do something clever, and yeah, let's do it anyways. Energy before equals energy after. So here's the problem. The energy before is kinetic, right, when it hits the spring. But you have to be careful because there's also going to be some potential before it gets to the equilibrium point. So it's above the equilibrium point at that point, right? And that's equal to, on the other side, it's going to be kinetic energy. Now, why can't I solve this? Because I don't know how much it gets compressed. I don't know where that equilibrium point is, right? So I got to figure out where that equilibrium point is. So how do I figure out where the equilibrium point is? Oh, that's what it asked for. How much is the distance the spring must be compressed? I'm answering the wrong question. I said, what's the speed? Then that's what speed is. This is what is the distance at which it have its maximum speed? Well, that would be the equilibrium point, which is where the forces are equal to 0. So all this, a waste of time. Instead, what I should have done is I should have gone F net equals the sum of all forces, going this way, crossing all this out because it's a waste of time, solving the wrong problem. So MA is equal to, I've got KX pushing up, I've got MG pushing down, so I make that a plus. And then I just simply go mass is 2, acceleration is 0 at the point, which is right traveling to the middle, right? It's neither pushing up nor down. The weight's equal to the force of the spring right at that point. K is equal to 200. X is I don't know, minus 2 times 9.8. All right, 2 times 9.8. 2 times 9.8. Divided by 200 is 0.098. 0.098 meters is how far that thing is compressed before it stops accelerating downwards and starts slowing down, right? Okay. Determine the compression, maximum compression of the spring. Well, here's where things get interesting. That is the equilibrium point, but it doesn't tell me how much energy is burned. So I've got to figure out when the energy, this is what I was starting to do here, kinetic energy plus potential energy, because when it gets to the very bottom, it's going to have burned potential energy as well, is equal to the spring energy, right? Which is just energy of the spring. Okay, energy of the spring. Okay, so kinetic energy we solved for earlier would be equal to 1/2 2 times 2.97 squared. You could use potential energy. You go all the way back up here and just use potential energy plus potential energy. Once it's at the top of the spring, it's going to go down h, right? So that's going to be m, which is 2, g, which is 9.8, h, which is I don't know, is equal to the energy loaded into the spring. Well, the spring is going to pick up 1/2. It's going to pick up the K, which is going to be, in this case, 200. And then how far is it compressed? It's the same h as this one here, right? So h squared. And look, I have got a quadratic equation. Isn't that great? That's a great thing. Let's do a quadratic equation. So I've got 0 equals, how do we solve quadratic equation? We move everything to one side. Minus 19.6h minus 2.97 squared. How about, where's my pen? 8.82. I'm sorry, I'm off the page here. Okay, 8.82. So then I'm going to get up my handy dandy calculator, go equations, polynomial, second degree. I'm going to go 100. I'm going to go negative 19.6. And I'm going to go whatever I got for the previous one, which I can't read. Wasn't that good of me? Okay, so I'm going to type in 2.97 squared. Bam. It'll take care of it for 8.82 is what that was in the corner. Equals two imaginary solutions. Let me back up. Menu. I didn't put a negative in front of that. Negative 8.82 would make that a better solution here. And so I get it's going to go down. The height it's going to fall is 0.4107 meters. Okay, so the height is 0.1417 up. What's the amplitude of the harmonic motion? Well, if you think about it, we just solved to get this problem done that has 0.098 the equilibrium point. So this thing is going to go down that far, so it's going to oscillate how much? Point that. 0.4107 minus 0.098. It's going to oscillate up and down a distance of 0.3127 meters. Now, some of you notice there's a negative solution. If you take this number and you subtract off 0.098, you're going to get the other number that was the other spot. Okay, that's the two places where the energy would be 0. Okay, so just looking back at the spring situation, okay, the equilibrium point was 0.098. the spring gets driven down because of energy, because of the kinetic energy, you're dropping it with speed, gets dropped down to all the way down to 0.4107 below the regular thing, below the unstretched spring. So therefore, the distance amplitude would be the distance between the two, because it's going to oscillate around that equilibrium point. Okay, hard problem, super hard. Hope you're doing it well. Again, here we go.